LegoBoostVision is a Python application that turns a hand-drawn robot pet on grid paper into real movement on a Lego Boost Move Hub. I won't go into details about the code. About 2 weeks ago, I created Lego Robotics AI with Pybricks project and published it. So, in the video, I explained it in detail and even debugged the application. The application is similar but even simpler, so if you want to understand it better, you can watch the video I'll include in the description. In this application, you draw a path on a grid with start, save screenshot as input sketch, PNG, and the run host path. The application sends that image to OpenAI Vision, which reads the sketch and returns structured path plan as JSON with alternating straight segments and turns. Distances are in millimeters based on grid squares, and default 50 millimeters per square. Turn angles follow Pybricks conventions where positive means left and negative means right. That JSON is validated with pydantic models saved under output and, injected into Pybricks drive-based template to produce generated path drive Python file. So the host then hands the hub over the Bluetooth, uploads the script and run it so the robot follows the drawn path. Stride, stride speed and turn rate are fixed in the template rather than read from the sketch. So GPT 5.5 performs very well at detecting paths and angles from images. We will start the application by running the host path. It will generate the JSON and the robot code will be generated based on this JSON structure. In this case, I will use the sketch PNG file where we have only 90-degree angles. When the application is deployed, you will see the robot running. However, the movement will not be perfectly precise in real life. Factors such as friction, wheel material, floor type, and even battery level can affect accuracy, so the robot may not always move or turn exactly as calculated. So we can fine-tune the robot movement by adjusting parameters such as stride speed and turn rate using the robot settings. These settings control how fast the robot moves in straight lines and how quickly it rotates. Higher values make the robot faster but less precise, while lower values improve control and accuracy. Note that once you deploy the code to the hub, the program is stored on the hub itself. You can then disconnect from the computer or tablet and run the program directly from the hub, allowing you to take the robot anywhere and run it without maintaining a Bluetooth connection. We will do it once it's deployed and running. I will run it again by clicking the green button on the Move Hub, and it will run it independently again. I'm starting the application by running host path. The JSON is generated, then the robot code is generated based on it and deployed. Let's first understand the JSON to see if the AI generated it correctly. So the first object represents a straight movement with distance of 200 millimeters, which is correct because 1 square is 15 millimeters. This also matches the calculation 4 times 50 equals 200. So the second object is turn. This means 90-degree right turn. Because in our system, plus 90 is left turn, minus 90 is right turn. So this is correctly interpreted as a right turn of 90 degrees. The third object represents a straight movement of 350 millimeters, which is correct because there are 7 squares and 7 times 50 equals 350. The fourth object represents the fourth object is turn. So this represents 90-degree turn, and it's positive this time because it's left turn. So the fifth object represents straight movement of 115 millimeters, which is correct because it corresponds to 3 squares, and 3 times 50 equals 150. So the sixth object is turn. This represents 90-degree turn to the right because the angle is negative. So the seventh object represents a straight movement of 300 millimeters, which is correct because it corresponds to 6 squares, and 6 times 50 equals 300 millimeters. So the eighth object is turn. This represents 90-degree left turn, since the angle is positive. And the last one represents a straight movement of 250 millimeters, which is correct because it corresponds to 5 squares. 5 times 50 equals 250 millimeters. This is the code generated by the AI and deployed to the robot. As you can see, it matches the generated JSON used to create the code, and the JSON structure accurately reflects the sketch. You may notice that although we specified 90-degree turn, the robot didn't turn exactly 90 degrees in real life. As mentioned earlier, this is due to the several real-world factors: friction, wheel material, floor type, wheel alignment, and even the battery level can all affect the robot's movement, so it may not always travel and turn exactly as calculated. For example, if you observe that the robot consistently turns less than 90 degrees, you can compensate by increasing the program turn angle until the actual turn is closer to 90 degrees. In this demonstration, how I intentionally left the parameters unchanged to show the robot's behavior using the original values generated by the AI without any manual calibration. Let's run the robot one more time. Since the program has already been deployed to the hub, I only need to start it by pressing the green button. This is the second sketch, and as you can see, it has different angles instead of only 90-degree turns. We should see whether the AI can understand it and generate the valid JSON structure that the robot can execute. Let's start the application and observe the robot's movement. Let's see the generated JSON. First it starts by moving straight 250 millimeters without turning first. Then it turns 53 degrees, angle minus 53. It's to the right. Then moves 200 millimeters straight. Then turns 27 to the left and moves 335 millimeters straight. Then turns 63 to the left, moves 150 millimeters straight, then turns 90 degrees to the left, then moves 250 millimeters straight. Then it turns 45 to the left, then moves 183 millimeters straight, then turns 72 to the right, angle minus 72, then moves 224 millimeters straight, then turns 63 to the right, angle minus 63, and finally moves 50 millimeters straight. You can see that the generated robot code matches the JSON structure.